We shall next look at this case study. An alphabet sigma is given to us, which is a comma b, and we are asked to check whether sigma star is countably infinite. What is sigma star? All possible strings over sigma. So which means, and you have a string of length 0, which we say epsilon or empty, then string of length 1, which is a and b, then all strings of length 2, that is AA, AB, BA, BB, and so on. Then you have strings of length 3, and so you get something like this. And then strings of length 4, 5, and so on. We want to know, is this set countably infinite? So please note, one can list sigma star and list sigma star there are two different ways of doing it. One is lexicographic, or the way you see in dictionary ordering. The other one is called standard ordering. Either you can list them in lexicographic fashion or in standard ordering. So standard ordering is like this. You list strings of length 1 first, then strings of length 2, and so on. So this one is standard ordering. If you follow lexico, then leave empty, then you list all starting from A. Then you will have AA and things like that, right? And so you will list all strings with prefix A. After that only we will start listing things for which the prefix is B. Correct? That is lexicographic ordering. So like this it goes. Once you are done with this, you start doing things related to B. But if you do this one, right, this itself is infinite in nature. This is another infinite subset in nature. But this we don't want, and we want to focus on something called standard ordering. What that says is list strings of length 0, strings of length 1, strings of length 2, and so on. When you have multiple strings of length 2, follow lexicographic ordering. Okay, see all of them. So to list multiple strings, right? Multiple strings of some length, say 2, 3, and so on, then follow lexico ordering. You follow lexi ordering among this. Then you start listing strings of length 3. Within this you follow lexi ordering and so on. Correct? Now sigma star with respect to standard ordering, this is an enumeration as a bijection to the natural numbers, meaning I can map this to 0, I can map this to 2, this to 3, and so on. That shows that there exists a bijection between sigma star to n. So please note, when we looked at Q, on the face of it, Q will not tell you that it is countably infinite. Then we went for a representation which corresponds to Q, meaning Q and n cross n has got 1-to-1 correspondence. Subsequently, that model helps us to show that n cross n and n has got a bijection. So similarly, if you just look at the set sigma star, we may not be able to conclude that it is countably infinite. And when I bring in sigma star and the elements in standard ordering, then you see that there is a mapping to n, or there exists an enumeration of sigma star. So we will have to come up with an appropriate model so that mapping can be established, or bijective mapping can be established with n. So now, because of this, I can conclude sigma star is countably infinite. Not just that, because of the bijection, cardinality of sigma star is same as cardinality of n. And subsequently we know that this is same as I, and this is same as n cross n. What is this telling us? So this is telling us that all countably infinite sets are of same cardinality. Because of transitivity, I can show that sigma star is same as I, sigma star is same as n cross n, and so on. So all of them are having same cardinality, which is n itself. We shall next show this case study, very interesting, that the number of C programs is countably infinite. So when we talk about program, when we say number of C programs, it's all possible C programs, okay? And so some of them may be syntactically correct, some of them may not be, and some of them may give you segmentation fault. So we don't look at syntax error, logical errors, and so on. So all possible C programs that one can write is taken into account. We say that that one is countably infinite. Okay, so please note when we write C program, so if you look at any C program works with some alphabet. So works with some sigma. So we are allowed to use numbers. In fact, whatever you see on the keyboard, one can use it, right? Then you are allowed to have these letters. You are allowed to use special symbols and so on. So your sigma or is precisely your ASCII set of characters, and it's finite in nature. So it could be maybe 127 keys or some 100 plus keys. So it's finite in nature. Now look at a C program. So you may start with something like this. Then you write void main and so on. Okay. Then you start writing some programming part. So what I'll do is, let me rewrite this as something like hash include stdio.h, then void main, then you may probably declare something, then some computation might happen. So like this it goes. Finally you see, now you can see that this C program, you can see it as a string over sigma. When I say string over sigma, string is a collection of characters, and the characters come from sigma. Or put it in other words, this one is an element in sigma star. sigma star, it consists of all possible strings. In particular, this string will also be there, correct? So it consists of strings of length 0, strings of length 1, 2, 3 and so on. This may be a string of length maybe 1000 characters. So when you start listing strings of length 1000, you will eventually list this program also. So that shows that this one corresponds to and this one corresponds to a string and it's an element in sigma star, correct? And this implies that any C program is a string. In particular, it is an element in sigma star, correct? And it's other way also. You can take a string and you can save that as a C program. So there is a one-to-one. It may not be syntactically correct. It may not be logically correct. So all that we are not seeing it. I am writing a text and saving it as .c. So if you see that way, C program is an element in sigma star. You take any string that corresponds to some C program. So you see that there is one-to-one correspondence between these two. Okay. So this implies that there exists a bijection between sigma star to number of C programs. Okay. So that shows that number of C programs is countably infinite. Okay. So there is one more way of doing this. So you can also look at it this way. You take a C program and that C program you can look at the underlying binary file. It consists of characters and so when you represent them, the system actually represent them using zeros and ones, right? So C program is an equivalent binary file, which means this one works with 0 and 1. So when we say number of C programs and it's related to so many binary files and they're all working with the alphabet 0 and 1. Now imagine you are trying to list 0, 1, meaning you are trying to list sigma star over the alphabet 0, 1. That shows that each of this corresponds to a binary string, and so you list 0, then you list 1, then you list 0, 0, you list 0, 1, very similar to what we did for AB. Like this it happens. And now each of this corresponds to some C program and may not be syntactically correct. And similarly, C program corresponds to this thing. You see that there is a one-to-one correspondence between these two. Therefore, the number of C programs is countably infinite. So one can look at the program, its underlying binary file, and establish a mapping between that and the natural numbers following the standard ordering of sigma star. So look at program of this form. So my first program and consists of say print say 1. And second program, I mean appropriate syntax. So you write printf %d, following C syntax you print 1. Second program it prints 2. And like that, if you look at program pi, it actually print I, and it goes. So now you can look at this one. So this says each one is a valid C program. Each one is a valid C program, and this corresponds to first natural number, second natural number, and so on. And that shows that number of C programs is infinite. See, the reason is I am not listing all possible C programs here. I am taking a specific case study where I am printing 1, in the second program printing 2, ith program printing I. Now this has got a mapping to n. So number of C programs with this number of C programs with this constraint, with the above constraint, meaning it consists of just one statement, print 1, print 2, and so on. With the above constraint is countably infinite, as you have a bijective mapping between you list all programs p1, p2, and so on, and that is mapped to ith natural number. Okay. Now, number of C programs with this above constraint is countably infinite. In particular, it is infinite, which means this one is a subset of all C programs. Correct? Now, you will have some other C program which has got another 10 print statements and so on. So this consists of, this is a subset of all C programs, which means a subset is infinite. So superset is infinite. So please note, subset is countably infinite, but superset we don't know. With this argument, I cannot conclude superset is also countably infinite. We don't know. So with this argument, I can only say number of C programs with the above constraint is countably infinite. In particular, it is infinite, which is a subset of all C programs. Therefore, the set of all C programs is infinite in nature. Okay, that's all I can say. Okay. Now I am going to merge this argument and this argument. Fine. Now all C programs, they are subset of sigma star. Just now we have seen, right? A C program is a string over this, which is an element in this. So which means all C programs is precisely a subset in this. And we know that sigma star is countably infinite. And number of C programs is infinite, and its superset is countably infinite. When superset is countably infinite, you can conclude that number of C programs is also countably infinite. Okay. So let me repeat this part. This is argument number 3. Argument number 1 is this. Argument number 2 is using binary file argument. Argument number 3 is you look at specific C program, meaning program printing exactly one variable, print 1, print 2, print I, and so on. And I don't have any other statements. So now this is a C program with some specific constraint. You see that this one is countably infinite, and this is a subset of all C programs, which means if a subset is infinite, its superset is infinite. I can only conclude that set of all C programs is infinite in nature. But at this point in time, I cannot conclude it is countably infinite. For that, I am bringing one more argument. So we know that each C program is a string in sigma star, so which means set of all C programs is basically a subset in sigma star. And using standard ordering, we have shown that sigma star is countably infinite. So if a subset, if a superset is countably infinite, and the subset which is infinite in nature, it has to be countably infinite. And that shows that number of C programs is countably infinite in nature. And so we have given three different arguments to show that set of all C programs is countably infinite. So very interesting part, it is because of this the computer science, in particular theoretical computer science, started showing interest in the field of infinite sets. And there are other interesting case studies like number of solvable problems, how many inputs are there to the sorting problem, how many different graph inputs are there to problems such as shortest path, and so on. And so these are all case studies that we come across in computer science. And so therefore and understanding infinite sets and its applications are vital as far as theoretical computer science is concerned. We will see more about this, and we will also start discussing uncountable sets.